So we have two more examples to wrap up section 1.2 here, and we're going to jump in with number 3. So we're going to translate into math symbols, and then we're going to decide if the statement is true or false. All right, so we're going to be doing a few translate problems as we kind of move through this first chapter or two, and then hopefully that's a skill that we build on to solve word problems, application problems. So first, just kind of reading from left to right. So 0, okay, great, we can do that, right? So 0. Now here's what's important on this one. The phrase is along with the less than. So is less than, that is going to be our inequality symbol. And so that's the less than symbol. Now it's important to realize for later, if it's just less than by itself, without the is in front of it, that's going to indicate subtraction. So that'll be something different we'll be on the lookout for. But this one has the is with it. So is less than, that's the inequality symbol. Negative, okay, well I know what a negative looks like. And then it says the absolute value of something. Okay, well, absolute value bars, I know what those are. So absolute value bars. And it's the absolute value of the number 10. So it's the absolute value of 10. So here's what I have. I have 0 is less than, and let's evaluate this over here. So we have these absolute value bars. The number on the inside is simplified. The expression has been simplified down to one number. So when we evaluate the absolute value of 10, it's just 10. The distance from 10 to 0 is 10. Remember, like number 2 up above last time, when a negative is in front of the absolute value, it's just kind of getting carried along and it gets brought down. Okay, so here's our statement that we want to be thinking about. Now, we want to think about this statement, 0 is less than negative 10. So we want to think about if that's true or false. So again, if you're struggling thinking about something like this, think about your number line. So number lines can be helpful in deciding things with inequalities. And it doesn't have to be perfect. I mean, here's 0, and maybe somewhere over here to the left of it, obviously, would be negatives, so negative 10. So as we look at something like this, 0 is to the right of negative 10. So that means 0 is actually greater than negative 10. It's not less than. So that statement, as we think about kind of the position of these two numbers on a number line, that tells us that this statement is false. So this was a false statement. All right, last couple of examples here. First, again, true and false. This time I also have some directions. It says something about if it's false, to give a counter example. So a counter example will just be one example, like one number, that's going to show that the statement's false. If it's false, that's what we want to give. So let's take a look. Part A, all rational numbers are integers. So all rational numbers are integers. So let's scroll back up and recall these two sets of numbers from our first video. So the statement again says all rationals are integers. So as I'm looking here, is it true that every single number in this rational category is going to also be down here in this integer category? Well, certainly not. They got that backwards if they were trying to come up with a true statement. There's lots of rational numbers in this list here. Things like 2/3, for example, that aren't integers. And those are going to be what we talk about as a counter example. So let's go back down to this problem here, and let's now answer. We know that this is false. So we just looked back at our definitions and saw that this was false. And now we can provide a counter example. So the counter example here is any rational number that's not an integer. So a counterexample here, 2/3 would have been fine. I'm going to give 1/2. Let's say counterexample of 1/2. And so the reason it's a counterexample, you wouldn't have to write it out, I'll just put this in parentheses, is because 1/2 is definitely in our rational category. It's rational, but it is not an integer. And so that's why this is a counterexample. So it is rational, but it is not an integer. So that would have been our counterexample. All right, part B. All irrational numbers are real. Well, if you remember, I kind of said everything that we're working with is real, so you bet. Let's look back here. So it's saying that every number that's in this category, the irrationals, is also in that category, the reals. Well, that's true. That's the nature of this tree diagram here. So yeah, everything we're talking about is real. So yes, all irrational numbers are definitely real. So that is a true statement. And if it's true, we're not asked to do anything else here. I mean, there is no counterexample if it's true. So that's true. All right, so that wraps up section 1.2. When we come back in our next video, we are going to start section 1.3, which is a lot of fraction work. Good old fractions. So that's what we'll start with next time.